So our final speaker for this session is Milad Eskandari, and he is at the University of Guelph.
No, that's okay. It's still morning. Good morning, everyone. And thank you, organizer, for this opportunity. Today, I'm going to talk about the modeling soybean yield from its components using machine learning and optimization algorithm. So this study is a part of the PhD project of my former students, Dr. Mohsen Yousefzadeh Najafabadi, who is behind all the data collection and analysis. So I know that it's going to be limited time. So I'm from Canada, University of Guelph. University of Guelph has two soybean breeders, Dr. Ishvan Raichan, my mentor, and my colleague, who should be in the room, who is responsible for early maturing soybean maturity group 0021, and my own program center in Ridgetown, focus on maturity group 1 and maturity group 3. So we work on conventional soybean and using biparental crosses, and yeah, it's a major activity soybean breeding program that we have. We recently developed a magic population, the first magic population for soybean. For those who are not familiar with magic, multi-parental advanced genetic intercrosses with its 8 founders that we use. And it has over 1,000 recombinant inbred line, and from them, over 700 are genotypes. And the goal is to make the population available to soybean researcher in next couple of years. So Canada is the 7th largest soybean producer in the world, with just over 7 million tons soybean production, and Ontario is the largest province for soybean and the first with producing about 50% of the soybean. So the goal in Canada is to reach 10 million tons by 2028. So one way for us to do that, to improve the yield and genetic gain. So, but we know that the genetic gain in soybean, in terms of the compared to maize and even wheat as a self-pollinated crop, is relatively low, and so study shows that it's about 1.3%. So, however, it's changed from regions to regions and maturity to maturity zones to maturity zone. But as you can see here, the several study from 00 maturity 00 to maturity 7 shows about 10 to 33%, 33 kg annual kg per hectare genetic gain. In our own study at University of Guelph, done by Dr. Ishvan's people, his former PhD student, Dr. Bros. So we measured the genetic gain in several decades. And as you can see here, the green dot are those active germplasm from his program, and genetic gain estimated is just over 17 kg per hectare per year. So, and for my own program, from my own program, red dots are the just about 16 kg per hectare. So, and the blue dots are historical lines. So this estimation is just from the active germplasm that we have in our breeding program. So theoretically, one way to improve the genetic gain is just to break the complex yield to its components, and hopefully those components are strongly related with the traits, and also they are not as complex and yield. So in this graph just showed, I just want to make sure that I make yield as complex as possible here. So for those that you are not familiar with the yield components in soybean, this graph shows the main components of yield in soybean from number of nodes per plant, number of pods per plant, number of seeds per pod, and seed size. So in this study, we use number of nodes, reproductive and non-reproductive nodes, and number of pods per plants, as well as the ratio of number of pods to number of nodes per plant to estimate the predict yield. So, and for collecting those data, we use my own germplasm, the core germplasm in my breeding program, 250 germplasm, and we planted in 2 locations, Richtown and Palmyra. If you see the Canada map here, this yellow part is Ontario, and we are located in southwestern Ontario, which is an important zone for soybean production in Ontario. So we planted here in 2019 and 20 using the RCBD with 2 rep and collected data from those information. And to predict it from those components, we use 3 different machine learning, the radial base function and multi-layer perceptron, which is the very well-known deep learning algorithm from the neural networks category. And those methods are used for the study or identify the linear and nonlinear relationship between inputs variables and output variables. So RBF is simplest and easier to train because of the simple and fixed 3 layers of input, hidden, and output layers. But multi-layer perceptron is a bit complicated because it has 2 or more 2 layers for that. We also use random forest as a very common machine learning algorithm for different areas, including breeding. So which is an ensemble of the decision trees, independent decision trees, that is different class compared to the previous machine learning. So, and in addition to individual machine learning, we also use the ensemble bagging one of the combine these 3 machine learning to see if we could improve the accuracy of the model. And in this model, all those 3 machine learning are trained independently at a parallel system, and after that, the results are somehow averaged to get the final product. So before going to the result, I would like to just take a look at the data that we have, the nature of the data that we have. The first, this heat map shows the relationship between yield components and yield, and also the relationship among those yield components. And as you can see, the yield has a strong relationship with all the yield components, positive relationship with yield components, except the number of non-reproductive nodes, which this trait is also negatively associated with the other yield components. So the reddish, it's the positive, and green is the negative correlation between these. So correlation between other components is somehow positive, a strong or moderately a strong positive correlation. And also the variability of the and heritability of the yield and its components. So this graph shows on y-axis shows the yield, and on x-axis we have those genotypes that we have. And each bar shows the variability of the yield production for each genotype across 4 environments, and those x's or crosses shows the average for each genotype across 4 environments. As you can see, the variability is, so for each and every of those genotypes are quite high, and heritability is 24%. When you go to maturity, as you can see, the variability is less and heritability is higher. And also the same here for number of nodes per plant. As you can see, the heritability is 34, and variability across environments for those genotypes is at least less than the yield. So, and going back to the goal, we are looking for traits that they are actually more heritable and less variable, affected by environmental factors. And the same here for number of nodes, reproductive nodes, and heritability 33%, and some level of variability. It's the number of non-reproductive nodes, 31% heritability, broad sense heritability, and also the somehow variability, and the last trait is number of pods per plant, which is most important components for yield in soybean, which unfortunately the heritability is still higher than yield, but variability, as you can see, is high, and you will see later the effect on that on our analysis, at least from my perspective. So having said that, let's take a look at the performance of accuracy of prediction using those machine learning. These three machine learning, those are individual machine learning. As you can see, we use coefficient of determination R square for as an indicator of the accuracy. And as you can see, the RBF with 81% R square, it's slightly better than RF and MLP. So, and when you take a look at the mean absolute error and root mean square error as indicator of the error associated with this estimation and prediction, you will see that, yes, the RBF has a lower MAE and also RMSE compared to this individual. So take home message, those all three machine learning, they perform relatively good, but if we have to pick one of them, is RBF has a better estimation. So ensembling and combining this machine learning together, we did that to see if we could improve the prediction accuracy. And as you can see here, we improve it. This is the ensemble or combined triggers. As you can see, 82% accuracy. We were able to improve the accuracy slightly better. And also, when you take a look at the error associated with those estimations, you can see that we are able to reduce MAE and RMSE. So take-home message or take-away message from results up to here is that the yield components are strongly related to yield, and also they are more heritable and less variability, less affected by environment. So they can be used for estimating yield in soybean. And also machine learning algorithms are successful and useful to predict the yield or estimate the yield. And of course, the ensemble algorithms is recommended and might be performed better. But the problem here, how I want to use this information in applied plant breeding. Myself, I deal with about 15,000 F1 hedgerows every single year to pick 15% of the advanced lines. So most of my former PhD students just took some time did some simple calculation about the amount of time he put to measure just number of pods for each genotype, which is 10 plants for this. He dealt with 2,000 plots and 20,000 single plants, and he calculated that he put 1,000 minutes to measure that, which is about 1 month, 8 hours per day, working days. So it's not applied information. It's good, but how we could use it. So having said that, we decided, okay, how we could use this information. We decided to design or model a high-yielding ideotype in soybean and see what is the optimum value for those yield components, to see if we have that, is there a way that we could use this information to pick complementary parental lines to make more promising crosses. So instead of going to progenies, go and select the smart parental lines for a smart promising design. So for that, we link the ensemble bagging algorithm to the genetic algorithm, which is one of the optimization algorithm, and it's derived from the natural selection or natural selection, in which that the more frequent variables are more successful that. So through this process, these random genotypes from the population are selected, and the progeny, some progeny design, and go back and use machine learning to actually estimate the yield components and optimize those components. So doing this, we were able to design an ideotype with a 5.64 tons per acre, about 83 bushels per ton, 83 bushels per acre, that in which the yellow part is the optimum value for those yield components in this study. So to just make sure that those are in the range based on the data that we have, this third row shows the range of variation, those traits in the population, that all of them are in the range. And I also asked Mohsen to provide the range for 5 best genotype that we have to see what is here. Everything is good except the number of pods per plant, which, as you can see, optimum value based on this prediction is about it's 49. But when you can see 5 genotypes, it's over 60 up to 70 pulse visits. So what was what is going on? So one answer is maybe 5 best genotypes among 250 is not a good number. It's not really a good representative of good lines. And another thing is that so if you go back to the variability and heritability of this trait in the data, you see that the variability is high, so these data by itself, they are not really the machine, the training method for that. So, and when we go deep and saw these 5 genotypes, the range of these variables is from 20 pods among these 5, 20 pods per plant, all the way to 82 pods per plant. So I think it's a good support for other speakers I mentioned for using those neural network. We need to have a large data to make sure that the training is accurate. So anyways, we hope that we have started to work on selecting parental line based on this information and create the population to see actually if any improvement will happen. So highlights from this study is the yield components seem to be promising and reliable to predict yield, and machine learning algorithm could facilitate this process, and also optimization algorithm could actually help us to find the optimum value for that. But there are some limitations that is recommended. So first of all, we decided to generate more data on this genotype to see how we could evaluate this, and also for sure more study on different genotypes and environment would be helpful. And the third part is coupling this information with the molecular marker technology to actually create the genomic tools, selection tools, to select for these traits at early age, generation, and not necessarily do the physical. For this, a study is ongoing, and we actually use the haplotype-based genomic selection using machine learning method, and by using that, we were able to actually have a good prediction compared to a SNP marker, molecular markers, increase the prediction model up to 5%. And this slide is interesting that we could find a haplotype on chromosome 19 with just about 1.8 million base pair that contains 69 SNP. And this haplotype is associated with all yield and all the yield components traits, and it contains 12 candidate genes, putative candidate genes, that I believe that it's a very good actually start to create the molecular markers from these to select for those. It's just an example of the potential of using those information for designing genomic tools for selection and that. So it's this publication is under review and hopefully we will publish soon. So by that, I would like to thank you, Dr. Raichan, and his team, that we really have a strong and close collaboration with them, not only on this, on several projects, and also Dr. Dan Talbot from Department of Animal Biosciences, University of Guelph, which is actually help us for machine learning analysis, and also, of course, my crew and my team at Ridgetown campus at Sparser. Thank you for your attention.